Okay, so today we're going to talk about section 8.5 on partial fractions. So we're going to have several cases here. So the very first case I want to look at is one we kind of discussed before. We talked about long division. And so let's look at the first example. And remember when I use long division. I use long division if the degree of the numerator is equal to the degree of the denominator, or if the degree of the numerator is larger than the degree of the denominator. So I'll say try when the degree of the numerator is greater than or equal to the degree of the denominator. And so for example, here's a case where I would use long division. Let's say I've got x cubed plus x over x minus 1, and I want the antiderivative, right? I want to integrate here. So you'll notice that the numerator is degree 3, right? It's a degree 3 polynomial. And the denominator is degree 1. And so, yeah, the degree of the top is larger than the degree of the bottom. So we're going to divide first. So step 1 is long division. Okay. And I want some placeholders here, right? Because this goes from the cube term to the x to the first term. Let's have some placeholders so everything lines up nicely. So I want x cubed plus 0x squared plus 1x plus 0. And this is being divided by x minus 1. And so here you have to remember from pre-calculus how to long divide polynomials. What you do is you look at the first term and you say, okay, well, this goes into this how many times? That's the same thing as asking this times blank equals this. Well, this times x squared equals this, and that x squared can go anywhere up here. Okay, and just like when you divide numbers, you're going to distribute or multiply, then subtract. Because really what you're doing is you're taking this many groups of this from this. Even if it's something that involves, abstract x's, we're still taking this many groups of this from this. Okay, so you're going to multiply and then subtract. So I've got x cubed minus x squared, and then I subtract. Okay. This minus this is 0, that's nice. This minus minus is plus. And do you notice how this has two terms? I would like this to have two terms. So this I'm going to carry down. Well, if that made sense, you're just going to do the same process again. You're going to look here, and now you're going to look here at the first terms, right? So, and you say same thing. This times blank equals this. Well, that times x equals that. Okay, so again, this times blank equals this. It's x, so plus x. And then again, you're going to multiply and then subtract. So multiply, you're distributing, and then subtract. Okay, this minus this is 0. This minus this is, well, 2x. And same sort of idea. I mean, this has two terms. I know it might be a bit silly to carry down a 0, but just for the sake of having placeholders, not a bad idea. Two terms, two terms. Okay. Well, this is round 3. It's more of the same. You look at the first term here, and you look at the first term here, and you say, well, this times blank equals this. That's 2. So that times 2 equals that. You're going to multiply, and then you subtract. So multiply, subtract. That leaves me with a 2, and that's a constant. We know that the degree of a constant is 0. Well, anytime the degree of this is less than the degree of this must be a remainder. So remember how to write your remainder? You write it as plus your remainder over what you're dividing by. That tells me something nice. It tells me that this, which was initially too difficult to integrate, is actually equal to this, much easier to integrate. Okay, so let's actually say that. Okay, so again, this, which initially, right off the bat, was too difficult to integrate, is equal to this much nicer form that we got by long division. Okay, and we could just go ahead and integrate term by term by term. So the first term, by the power rule, I get x cubed over 3. The second term, by the power rule, I get x squared over 2. The third term is 2x. And here I've got a natural log. Plus c completes the problem. Okay, so I hope that made sense. I want to go into now the cases of partial fractions. So the question is, okay, we know what to do if the degree of the numerator is bigger than or equal to the degree of the denominator. But what if the degree of the denominator is bigger? What are some things we can try? And so for partial fraction decomposition, this is really case 1 of partial fractions. And so let me sort of demonstrate through an example. Let's suppose we have the following. Let's suppose we have the antiderivative of x plus 5 over x squared plus x minus 2 dx. And so very often when it comes to fractions, you're used to taking two fractions, getting common denominators and adding them together to make a single fraction. Well, with this technique, you want to do the opposite. You want to take a single fraction and sort of break it apart, rip it apart into smaller fractions that are easier to integrate. So the question then becomes, well, how do I break this into smaller fractions? You want to use this technique. You need to use this technique. Okay. So step 1, we're going to do some algebra. You want to factor the denominator. I'm not concerned with the numerator. Let's factor just the denominator. Okay, so that factors nicely to parentheses x minus 1, x plus 2. Now I want to classify each of these factors. There's sort of a special name we give them. The first thing I want to do is sort of look at the x term. Notice it's to the first, so we call that linear. When x is to the first, that factor is linear. Okay, so x is to the first, we're going to call that linear. And then you look at the exponent on the parenthesis to see how many copies, in a sense, you have. In this case, the exponent on the parenthesis is 1. So we have exactly one copy of this. I'm going to call that unique because it doesn't repeat. It's not like it's squared and there's 2 copies. So since there's just one copy, I'm going to call it linear and unique. Okay, linear because x is to the first, unique because there's only one copy of the parenthesis because of exponent 1. So that's a special classification. Notice here, let's classify this as well, and you'll notice the same. It's linear because x is to the first, and it's unique because there's only one copy of the parenthesis. So linear, unique. So once we realize that, this is how you want to decomp linear unique factors. You want a constant over the first factor plus a constant over the second factor. Okay, so hopefully this sort of shows you the direction that we're going. We're trying to take a single fraction and split it into little bite-sized pieces that are much easier to integrate. In order to do that, I need to solve for a and b. So that's my next goal, solve for a and b. In order to solve for a and b, I'd really like this not to be a fractional equation. So let's get rid of all these fractions by multiplying by x minus 1 times x plus 2. That's, what do we call that? The least common multiple of all the denominators. That's the smallest object that all these denominators will go into without a remainder. Or in easier terms, it's always just that. So what you want to do now is you want to distribute this. And again, we're hoping to cancel out these fractions, right? So I've got x plus 5, right, from here. And again, I'm distributing this here, here, and here. Okay, so we've got a times x minus 1, x plus 2, and then b times x minus 1 times x plus 2 over x plus 2. So yeah, I really did just distribute this to all three terms. Notice the canceling that's going to happen. That's the entire point of multiplying by this. The canceling is going to get rid of all the fractions. Exactly what we were looking for. Okay, so this, anything over itself is 1. So those will cancel. And so we're left with this. Looks like we're left with a times x plus 2, b times x minus 1. This is the equation we're going to use to find a and b, because again, we're looking for these constants a and b. Okay, so I'm hoping that seems fine so far. And so the question then becomes, well, how do I get my hands on those constants a and b? And here's the idea. This is an equation, and it's an equation that's true for every x. For example, if I plugged 1 in for every x, that'd be true. If I plugged 10 in for every x, that'd be true. This equation holds for all x's. That means if I'm clever, I can choose convenient x's that make terms drop out so I can solve for the other terms we're looking for. For example, if I want to solve for a, what choice of x would make this term drop out so I can solve for a? Well, if x is 1, you're going to get a 0 here. That would make that drop out so you can solve for a. Let's say that. So if x is equal to 1, again, plug that in for all the x's. That's why it's legal, because this holds for every x. And if I pick an x, I have to, plug it in for every x. So 1 plus 5 gives me 6. So I'm plugging 1 in here. That gives me 1 plus 2 is 3. And that'll vanish. That's exactly why we chose 1. We wanted that to go away so we could find a. So divide by 3, and it looks like a is 2. So that's nice. Our next goal is to find b. And it's really the same game, right? So what choice of x would make this drop out so that I'm able to solve for b? Well, if x is minus 2, that's going to be 0, allowing me to solve for b. Okay, so if x is minus 2, so plug in minus 2, that's going to give me 3. And then, so plugging in minus 2 minus 1 is minus 3. And so it looks like negative 1 is equal to b. We found both of our constants, which means we're able to decompose our original fraction into these little bite-sized pieces. So this integral will be equal to the integral of this. Much easier. Okay, so let's say that. So our original expression is equal to, well, let's think about it, right? So it decomposed into a over x minus 1. So I'm going to plug a, what do we have for a? We said we had 2 for a. So we're going to plug 2 in for a. So that's a over x minus 1. And then we said we have minus 1 for b. So we're going to plug in minus 1 for b. And that's over x plus 2. And of course, you can check your work. If I combine the fractions, I'm going to get that back. I don't want to combine them because this is easier to integrate than this is. So now you notice, okay, well, I just have to integrate the pieces, much easier. So this is a natural log form. So this is 2 times the natural log of absolute x minus 1. And I do need the absolute value here, minus the natural log of absolute x plus 2 plus c. I could combine these using log rules. It's not necessary. This is perfectly fine. Okay, so just a short recap. Okay, so just for a moment, forget about the calculus, forget about the integral. Take this expression and factor the denominator, and then classify. This is linear, unique. This is linear, unique. And the way we decompose linear, unique factors is a constant over the first factor plus a constant over the second. We didn't want the fractions, so to get rid of the fractions, we multiplied by this. After we distributed and canceled, we ended up with something that was a lot nicer, namely this. We then choose convenient values for x that allow us to solve for a and b individually. If x is 1, this will drop out, and I can solve for a. If x is -2, this will drop out. That allows me to solve for b. Once I have a and b, rewrite your original integral like this by plugging a in for a and b in for b, and simply integrate. Okay, let's look at another case. So what happens if we have repeating factors? So we'll call this case 2. So linear repeating factors. So for example, let's say we have something like this. So the degree of the numerator is 1. The degree of the denominator is 2 because after you square it out, the highest exponent is a 2. So it's not long division, right? So we're going to try partial fractions, and let's see what I mean by linear repeating factors. Okay, so we're going to deal with the algebra. We put the calculus on hold. Well, first of all, we check and see if this is factored. It's already factored. That's nice. Notice that x is to the first on the inside. So that's considered to be linear. And then the 2 means it's repeating. There's 2 copies of the same thing. So we call this linear because x is to the first. And repeating because there's 2 copies of it. It's not unique. There's 2 copies. So the question then becomes, well, how do we decomp linear repeating factors? Here's what you need. You need a constant over a copy to the first plus a constant over a copy squared. What you're doing is you're leading up integer power by integer power till you get to the ultimate power of 2. If this were power 4, I would need a over this to the first, b over this squared, c over this cubed, and d over this to the fourth. Do you see how you sort of account for every power from 1 to the ultimate power? Okay, so that's how to deal with repeating factors. And the rest is, it's really more of the same. Okay, so we're going to distribute and cancel. Let's see if we can save a little time when we distribute. And so at the same time, let's distribute and cancel. So if I just distribute here, notice this would cancel with this. That would leave me with 5x minus 2. Now if I distribute here, notice that just one copy is going to cancel. That leaves me with a times x minus 2. And then here what you're going to notice is that both copies cancel, and I'm just left with b. Okay, so what did I do? I distributed and I canceled really at the same time. Well, if I want to solve for a, I don't think there's a nice choice of x that makes this drop out. Okay, we'll talk about how to deal with that. Let's solve for b. What choice of x would make this drop out so I can solve for b? Well, it's got to be x equals 2. So if x is equal to 2, plug that in for all the x's. That's going to allow you to solve for b. So if x is 2, that's 10 minus 2. And that gives me b. So yeah, the idea is you choose a convenient value of x that makes something drop out so you can solve for the other constant. Well, then the question becomes, how do I find a? Well, once we're stuck in a case like this where we can't find a, what you want to do is expand out your algebra. Okay, so expand out your algebra. So that gives me 5x minus 2 is equal to ax minus 2a plus b. And there's sort of a clever observation we want to make. I mean, these are both polynomials of degree 1, sort of lines in a sense because x is to the first. And if these two polynomials are equal, then their coefficients must be equal. Let me show you what I mean. So if that's confusing, just think of the following, right? Say, for example, if I told you, that, mx plus b is equal to 2x plus 3, you would have no problem saying that m is equal to 2 and b is equal to 3. That's what I mean by equating coefficients. If these are really equal polynomials, then they're equal coefficient by coefficient. So if I said, ax squared plus bx plus c is equal to x squared minus 4x plus, 10, you'd say, oh, well, a is equal to 1. See what I mean by equating coefficients? B is equal to minus 4. And you would say, well, hey, c is equal to 10. It's the same idea. It really is. It's the same idea. So if these are both equal, you should tell me that a is equal to 5. And all the constants are equal to the constant. Okay, so a is equal to 5 and minus 2a plus b. Did I write a equals b? Of course I did. Why wouldn't I? I wanted to say a is equal to 5. Happy Friday. Okay, so this is equal to minus 2. Okay, so equate coefficients. The coefficient of x must be equal to the coefficient of x. And the constant term, even if there's many added together, at the end of the day, that stands for a single number. The constants are equal to the constants. Well, I was just looking for a. You can actually check that this satisfies, these two satisfy this equation. This is, look, negative 10 plus 8 equals negative 2. So we've got the right constants. Well, what does that mean for us? It means that, well, integrating this, which was too tough, right? Too much going on, is equal to integrating this. Much nicer. So yeah, let's say that. So integrating this original expression, which was, well, too difficult, is equal to integrating this. Well, remember, a goes in for a and b goes in for b. So the integral of this is equal to the integral of this. So a in for a means that's 5. over x minus 2. And again, we're plugging b in for b. Well, b is 8, and that's over x minus 2 quantity squared dx. Because these require different techniques, I mean, this is going to be a u sub and this is a natural log, I'm going to split it up. Typically, I only split it up if they require different techniques. If you want to factor the 5 and the 8 out, feel free. That's not a problem. And yeah, I'm going to split it into sort of these two baby problems and then add their answers together at the end. Okay, so this one is, like I said, it's nearly instant. We recognize that as a natural log form from Calc 1. So that's 5 times the natural log of x minus 2, and I'm going to put a plus baby c. I know it's in the middle of the problem. That, hey, math guilt, it's a thing. So plus c, little tiny c right there. So for this one right here, we want to make a substitution. So let's let u equal x minus 2. And so du is equal to 1 dx. That seems really nice because what do we get over here? So I'm not going to forget my plus. Let's take that 8 out. We're going to get, so dx is equal to du. And downstairs, that's going to be u squared. So u squared. And we know to bring that up with negative exponents, so we can use the power rule. Remember, that's not a natural log if that's to the second power, only when the downstairs power is 1 on your variable. So that's certainly not a natural log. So bring it up with negative exponents, and then we'll use the power rule. So remember how to do that? We need to increase the power by 1 and then divide by that new power. My guilty plus c. Okay, so just doing my algebra, that gives me 8 over u. And then just plug u back in. So u, we said, was exactly this. So that's x minus 2. And then we'll combine the two answers together. So we get 5 times the natural log of x minus 2. That turned out to be minus when we integrated, minus, looks like 8 over x minus 2 plus c. And that was case 2. What happens if we have linear repeating factors? Okay, so now we move on to case 3 when we start to talk about quadratic factors. You know, factors with squares in them that won't factor or split any further. Okay, so let's try this. Let's try the antiderivative of 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4 dx. And I will label this as case 3. These are quadratic unique factor. So you might be looking at this and saying, hey, what's going on? This is not quadratic, that's linear unique, and that's linear unique. Well, it's very often the case that you have mixes of them all, to be honest. The quadratic unique I'm talking about is this. What makes it quadratic? It's squared and it won't factor any further. You always check and see if it can factor further. This is squared, it's not going to factor further, at least not over the real numbers, right? We're not going to use imaginary numbers in this course. So this won't factor further. What makes it unique? There's only one copy of it. So quadratic and it won't factor further. Unique because there's one copy. So how do we decomp that? Let's take a look. Okay, so yeah, let's classify the three factors. That's linear and unique. Linear x is to the first, unique because there's one copy. That's linear and unique. That's quadratic and unique. So first, let's talk about the linear uniques. They need a constant over what you're dividing by. That's how to take care of linear factors, factors with x's to the first. And then to take care of the quadratic factors, I need, you know how mx plus b is like the form of a line? You kind of want that idea here. So instead of calling it mx plus b, let's just call it cx plus d. And there is a bit of a pattern going on here. I want to sort of highlight that. Notice when the factor is linear or degree 1, we decomp it with a constant, which is degree 0. Degrees are off by 1. So when that's linear, we decomp it using a constant, degree 0. Well, when that's quadratic, we decomp it using a general linear, which is degree 1. So that's why cx plus d. Okay. So I'm going to multiply through by this. So that's x times x minus 1 times x squared plus 4. And you're going to see me distribute all the way through and cancel at the same time. So imagine distributing to all the parts and imagine what would cancel. Let's see what you're left with. Okay, so what did I just do? I took this and distributed it here, 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 and here, and canceled. So goodbye, 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 goodbye. That would stay with A. Goodbye, goodbye. That and that would stay with B. Goodbye, goodbye. That would stay with Cx plus D. Now we want to find as many of the A, B, C, D as we can. Sometimes we can find them all, and sometimes we can only find one or two. So let's see what we can do. So say I wanted to find A. If I wanted to find A, what choice of X would make this drop out and this drop out? It's going to be the same consistent choice of X. So if I want to solve for A, and that means I'm looking for this to drop out, what choice of X, here's your clue, would make both of those drop out? Well, if X is equal to 0, then this is gone and this is gone. That's going to allow me to solve for A. So if X is 0, so you can imagine that would drop out and that would drop out. Plug that in for every X, because remember this equation is valid for every X. And so if I choose an X be consistent, plug it in for all the X's. On the left, these drop out, I get minus 8. Okay, now here, if I plug 0 in, that's going to give me minus 1, right? 0 minus 1. And then here, that's going to give me 0 squared plus 4, which is 4. And so I think that forces A to be 2. So I'm pretty happy right now. I've got A. Let's see here. Can we find B? Is there a choice of X that would make this drop out and this drop out, allowing me to solve for B? Well, if X is 1, that's going to 0 out, and that's going to 0 out. That would allow me to solve for B. So let's choose X equal to 1 because it makes the terms we want to drop out and allows me to solve for B. So if X is 1, I get 2 minus 4 minus 8, which I think is negative 10. Double check me on that. Yeah, we're fine there. And then, okay, so if X is 1 here, that gives us, it looks like 5B. Right, I'm plugging 1 in for all the X's here. And so that forces B to be minus 2. Okay, great so far. So good progress. The only issue we're going to run into now is if I want to find C and D, there's not a choice of X, not a real number choice of X that would make these drop out so we could find them. So it seems like we're stuck. Remember when we did algebra before? That's what we want to do now. So we're going to expand all this out, so stay patient, and we're going to equate coefficients. Okay, so when it seems like you're stuck, you found as many as you can, expand out all the algebra. Now for this, let's expand out this. That'll help me a little bit. So that's x cubed. That'll be minus x squared. That's 4x minus 4. So I'll just need to distribute a over that. Okay. This right here, well, here this is not so bad. We can distribute the bx at the same time. That's not so bad. But for me, I'm going to expand this out because there's a lot going on here. A lot going on. That's x squared minus x. So here I'll use distributive property or FOIL or whatever you're calling it these days. I like to call it distributive property. Okay, so yeah, let's multiply all that out. Okay, so expand your algebra when it seems like you're stuck and you can't find any more of these constant coefficients. Okay, so on the left, we still have 2x cubed minus 4x minus 8. And then distribute your a. So you get ax cubed minus ax squared plus 4ax minus 4a. So what am I doing? Just distributing this a over all 4 terms to get this. Now I distribute bx. So if I distribute bx, it looks like I get bx cubed plus 4bx. That seems good. And here I'm going to distribute the cx over both terms and then the d over both terms. So that gives me cx cubed, right, minus cx squared plus dx squared minus dx. And I'm going to double check my work because if I make a mistake, it'll have a huge effect on this problem. Okay, happy there. And it only takes a moment to check. It's totally worth it. Good there. Okay, great. So I'm happy about this. The question is, well, how do I make any sense out of this mess of terms? Well, the answer is you want to organize them. So I like to put little symbols because it keeps me organized when I have a mess of terms. So for the cube terms, let's use this symbol. So all my cubes I can organize nicely. My square terms, let's just use a square. Okay, that keeps me organized. For my linear x to the first terms, let's just use maybe a little line segment. And then for my constant terms, is there just one? Let's use a star. That really helps me stay organized. Notice how the left doesn't have an x squared term. Let's put a placeholder there. That's going to be helpful in the end. So if there's any missing terms, a placeholder is very helpful. Okay, so first I want all my cubes. So there's a cube, there's a cube, there's a cube. So that really helps. I know they have 3s for cubes, but there's just something about having it organized like this I find very helpful. So I bring them together and I factor out the x cubed to the right. So it looks like a coefficient times x cubed. So here, here, and here, and I did a right factorization of x cubed. Let's do the same thing with the squares. So I've got negative a minus c plus d x squared. Okay, so I'm hoping that's okay so far. And then my linear terms, my x to the first terms, right? So I've got, looks like 4a plus 4b minus d x. And I just have a single constant, right? I think 4a is my only constant. And I think that's minus, isn't it? That's minus. There we go. Okay, so great. Everything is organized. My cube term, my square term, my x term, my constant. And so the idea is the same as before. If these two polynomials are equal, then they must have equal coefficients. Otherwise, they wouldn't be equal polynomials. So the coefficient of x cubed must be equal to the coefficient of x cubed. So a plus b plus c must be equal to 2. Equating coefficients. Equal. Same idea. The coefficient of x squared must be equal to the coefficient of x squared. So the coefficient of x squared must be equal to the coefficient of x squared. And if that made sense, this is more the same. The coefficient of x must be equal to the coefficient of x. And then you equate the constants. You want to use what you already know from before. So remember from before, we said a was equal to 2. That's helpful. B is equal to minus 2. So use those, right? You're going to use those to find B and C. Okay, so let's see what we can do here. Well, this is so nice, right? Because imagine plugging those in. If I plug those in, they're going to cancel. That's 0. So for free, I get C is equal to 2. And that's so nice. Okay, so A and B, plug them in. That gives me that C is 2. What else do we have here? So let's take a look. Well, we can easily find D, right? We know A and C. So negative A, you know what, for my sake, negative A minus C plus D is 0. That forces D to be 4. We have all our coefficients. We can finally integrate. So all that algebra was completely necessary, and you must show that in your decomposition. Great, so what's the game plan now? So the game plan now is we want to go back here. And remember, we said that this was equal to this. That means that integrating this is equal to integrating this, right? So we want to plug A in for A, B in for B, C in for C, D in for D, and integrate this. It's still much better than what we started with. These bite-sized pieces are more friendly than this monstrosity. So this technique is so valuable. If you take a course on differential equations, you'll use it again. It's so handy. Sometimes that course is called Calc 4 in some places. Okay, so here we go. So now, next goal, integration. So the original, which was too difficult to solve right off the bat. This is equal to, so remember, A over X. So A over X. Remember, we solved for that. So A over X. Plus B, well, that's minus 2. Over X minus 1. C we said was 2. And D, I believe we said was 4. Okay. Okay. So we have to sort of come up with a strategy for integrating. Well, both of these terms are natural logs. That's instant. The question is, what's going on here? So mentally, I always check for a u sub. If this is equal to u, its derivative does have a 2x, but that plus 4 is complicating things. The fact that this plus 4 is complicating things is sort of hinting that I might want to consider breaking the fraction up. That's a huge strategy with us. So if you go to do u sub, and it's helpful here, but not helpful here, break up your fraction. So this over this plus this over this. That's going to be very, very helpful. Okay, so what do we have here? So notice how I'm breaking up my fraction. You always break it up over the numerator. So the first term over the denominator plus the second term. It's really kind of like common denominators in reverse. Sort of been a theme today, hasn't it? And again, why did I do that? Because if I do a u sub and that's u, its derivative doesn't help with the plus 4. Therefore, split it up. Okay, we're going to break this into sort of bite-sized little baby integrals. Make it really manageable. Okay, so here's our first. This is 2 times the natural log of x plus tiny c, right? It's got the downstairs power is 1, so it's a natural log form. Downstairs power is 1, so it's a natural log form. I should write it out. Plus tiny c. This is going to be a u sub. Here the u sub is appropriate because if u is equal to the denominator here, its derivative is perfectly this. There's no extra plus 4 business, right? So this is perfectly a u sub. That's really nice. So that's equal to, well, du, right? That's du over u. Downstairs power is 1 again. So you should recognize this as another natural log form. So this is the natural log of absolute u plus tiny c. But you notice that u is positive, right? For any real number, this is positive. So we certainly don't want the absolute values. They're not needed. And this is something you want to recognize. This is our arctan form from day 1, right? So this is in the form of an arctangent. Again, I don't need to do a trig sub on this because we've studied this form before. It's not wrong to, it's just unnecessary. So that's u squared, that's a squared. So remember 1 over a, arctan of u over a plus tiny c. Those will cancel out and give me a 2. And let's give our final answer. We've earned it. So this is 2 times the natural log of x minus 2 times the natural log of x minus 1 in absolute values. This is plus the natural log of x squared plus 4, no absolute values because that's positive for every real number. And then plus 2 arctan or inverse tan of x over 2 plus c.
I didn't catch that. Please say that again.
I don't know if you heard that. That was Alexa. Okay, so that scared me. So we've got 2 times the natural log of absolute x minus 2 times the natural log of absolute x minus 1 plus the natural log of x squared plus 4 plus 2 times the arctangent of x over 2 plus c. Well, lucky for us, we only have one more case. You can see the need to practice though, right? Because there's a lot of variation. There's a lot of algebra to master. It's really, really important to sort of, give it its proper time. Okay, so case 4. So repeating quadratic factors. So here it's quadratic because it's squared and it won't factor further over the reals. And there's 2 copies. So quadratic won't factor further, 2 copies. Quadratic repeating. So how do we deal with quadratic repeating factors? Let's take a look. It's the same idea when we had linear repeating. Remember how we sort of led up to the ultimate power? You had a copy to the first, then a copy to the second. It's the same idea. Because they're quadratic, I'm going to need ax plus b. I'm going to need over a copy to the first, plus cx plus d over a copy squared. If that were cubed, I would need an ex plus f over that cubed. So you lead up to that power 1 by 1 by 1. Okay. Well, once you figure that out, it's really more of the same. Okay, so I multiply through by this, and that's going to kill all the fractions. So I can solve for a, b, c, and d. Okay, so you're going to distribute through. So you got x cubed plus 13x, because those would cancel. So 1 copy here would cancel. That would give you ax plus b times 1 copy of x squared plus 2. Again, because 1 would cancel. Plus cx plus d, and they both would cancel here. That's nice. And what you're going to notice is I can't use that nice startup trick of picking convenient values for x to find, a, b, c, or d. And I've only been picking real numbers. I'm not dealing with imaginary numbers here. There's some neat things you could do there, but we're not going to. So since it seems like we're stuck, remember the key is to do algebra. Okay, so distribute. So that's ax cubed plus 2ax plus bx squared plus 2b, right? So I just distributed, distribute, and of course, distribute. I'm going to check, always check. Happy, I'm happy, I'm happy. Excellent, so good. It's worth checking. It's always worth those few seconds. It really is. And I'm going to label just like I did before. So cube term looks like it's the only one. Square term, it's the only one. There's 2 linears and 2 constant terms. That keeps me organized. Okay, let's see what we have here. So 8x cubed plus 13x is equal to, well, there's only 1 cube. You know what? It might, again, I mentioned this earlier. You know what? It's not a bad idea to have placeholders on the left. There's no square term. Let's have a placeholder there. That's pretty smart. And there's no constant. Let's have a placeholder for that. Placeholder for the square term, placeholder for the constant. Okay, so I've got ax cubed, nothing for it to combine with. I've got bx squared, nothing for it to combine with, but I do have 2 linear terms. Okay, so that's 2a plus c, and factor out the x to the right. So that's the coefficient of x now. And I've got 2 constant terms, so bring them together as well. And now that everything's organized, you can equate coefficients. So for free, I get that a is equal to 8. That's good. And for free, I get that b is equal to 0. That's also nice. Well, not so free. I get that the coefficient of x equals the coefficient of x. So 2a plus c is equal to 13. 2a plus c equals 13. Let me move this out of the way. And then the constants must be equal to the constant. So 2b plus d must be 0. Okay, so use the information you know to find, c and d. If I want to find C, well, think about this, right? So A is equal to 8. So this is 16. If I subtract 16 from both sides, it looks like C is, I think, -3. And I can easily find D, because if B is 0, plug that in, that forces D to be 0. Again, just by plugging that in for B. Okay, so I'm really happy now, because I could take that information here, and this tells us that integrating this is exactly integrating this. So that seems quite good. So in for A goes 8, in for B is 0, in for C is -3, and in for D is 0. So let's plug those in, and then we'll integrate this. So integrating the original is the same as integrating, let's see here, ax plus b. So 8x plus 0. So 8x over x squared plus 2 minus, because c is negative, right? C is -3. So 3x over x squared plus 2 quantity squared. Okay, so ax plus b, but b is 0, and then cx plus d, and d is 0 in this case. So that's dx. So I think I'm going to split them up and then use a u sub. So yeah, maybe I'll split them into little bite-size integrals here. If you want to factor the 8 out, you can. Feel free. Nothing wrong with that. And then minus, right? And if you want to factor the 3 out, that's fine as well. Okay, so it's going to be a u sub, and I think the same u sub is good for both, because if u is equal to this, its derivative 2x helps with this. And same idea here. If this is u, its derivative will help with this. So it's the same sub for both. So maybe x is equal to, what is it, x squared plus 2? I'm sorry, that's u. U is equal to x squared plus 2. Du is 2x dx. Divide out the 2. And so I get 1/2 of du is x dx. Okay, so that's my u sub here. Okay, so let's see here. So this right here is equal to 1/2 of du. So how am I going to write 1/2? So 1/2 of du, and this is what we're calling u. Okay, that seems good. And then over here using the same sub. So this is what we're calling 1/2 of du. Okay, this is a natural log form. This is not a natural log form. Okay, this has a downstairs power of 1. That's why it's a natural log form. This doesn't have a downstairs power of 1. So I'll bring this one up and use the power rule. And this one we'll call 4 times the natural log of absolute u plus little c. But u is always positive. So that's 4 times the natural log of x squared plus 2. And then over here, this is what, 3/2? This is u to the -2 du. So we're going to integrate and then back sub, and then we'll put our answers together for the final answer here, right? So I've got 3/2. So I'm including this now, okay? So 3/2. This is u to the -1 over -1 plus c. Let's clean that up. Negative is positive, so that's 3 over 2u. Okay, so just rewriting my algebra here, right? U goes downstairs. The negatives cancel. This negative, again, if you're confused, it came from the minus from there. Okay, so finally, putting them together, my final answer is 4 times the natural log of x squared plus 2 minus Oops, plus, right? Double negatives. 3 over 2 times u. Well, we said u was take 2. Okay, here we go. That's real life, folks. That's how it goes. So this is 4 times the natural log of x squared plus 2 plus, right? Because that's all the negatives canceled. That's 3 over 2 times u, but that's u. That's a bit better. Plus c. Okay, so lots going on with the different cases. Make sure you're well practiced with each of them. Case 3 in particular is very common in calculus, so with the mixture of quadratic factors and linear factors. So definitely check that out. And yeah, I wish you luck. It's a very useful technique once you get it down. And yeah, good luck.